Ken Kittless in year 2000, and I told him about all my theory with the ratio trick and everything, and I told him about the beam split coincidence experiment. I knew that was the key, the beam split coincidence, but I didn't know which part of the spectrum to do it in. I was suspecting to redo that experiment with X-rays. And because I knew that they were looking at some kind of illusion with the beam split experiment, I recognized the polarized beam splitters that Clauser used, that it was a mistake. And I knew that experiment needed to be redone. I figured that out all by myself. I approached my friend Ken Kittless with all this information, and he immediately said, do the experiment with gamma rays. And I told him, well, I don't know anything about gamma rays. This was the year 2000, thereabouts. And I said, well, which gamma ray should I use? And he said, well, try sodium-22. It puts out annihilation radiation. And I didn't even know if you could buy it at that time. And he said, oh, yeah, you can just buy it. So I went and I took his advice. I figured out how to buy the isotope. I somehow put together a rudimentary way to do the experiment with counter timers. It was a very clumsy way to do it, where I measured the amount of time in between detector clicks and scintillators. And the experiment did not work. It just showed chance. But I kept working on it. And so I do take the credit, even though Ken told me to do it with gamma rays, and he was right. But we didn't know how to make it work. I made it work I kept working at it by finding another isotope that was more likely to work, that put out one gamma ray at a time. I chose cadmium-109, and I think it was year 2001 where I made the experiment show better than chance, and it was with a very similar detector that I sent you as the thin detector. I found a half-inch cylinder from Micron, and I went through the side of that, and I was barely able to see something above chance. And I tried some other detectors and kept working on it from there to perfect it. So that's the story where there's a friend of mine who gave me this important hint to use gamma rays.
I see, because there need to be some starting point. They don't pop up just in maybe sometimes people get there on their dreams, but you have and school and the work in physics and biology, and these ideas were rolling on your mind kind of 20 years.
Right.
From 80s to 90s.
That's right. I did a hell of a lot of work. I set my friend up with the question. He gave the right answer, and then I kept working on that answer, the gamma ray effect, to use gamma rays in the beam split coincidence experiment. And we found out, well, I found out from searching that nobody did it before. They did use gamma rays for something similar to a Bell theorem test with sodium-22. I found that. But they did not do a simple beam split experiment with gamma rays. I found that somebody tried X-rays. They did a whole bunch of library research trying to figure out, well, who did this with what? The beam split coincidence experiment. And so it's all in my references as to who did the earlier versions with X-rays and then visible light. and they just stayed with visible light. Granted, they did things with atomic beams and lasers hitting it to make pairs of their H news go in different directions. They used one as a trigger. So that was the work of Clauser, where he tried to make a triggered source one at a time, but he still saw chance. Then it was very similarly repeated by the French team, Grangier, whose paper you showed me, and Aspect and Rogers. I'll just call them the French team. They did several papers. They did the beam split coincidence and also Bell's tests and several others. So I think they're still working on it. And I looked at a lot of papers.
How did you come up with an idea that you should get something else than just a chance in the experiment? Kind of how did you know to wait that there's in doing some way this experiment you could expect more than chance? And related to this, of course, how did you realize some form of wave behavior of particles? Not particles, but waves could do that.
I knew the loading theory was correct without anybody telling me, just from the beam split coincidence. Just from the double slit experiment, just the simplest form of wave-particle duality, that I knew it had to be a loading theory. Straight away, that's what was causing the clicks to show up, because we knew waves had to go across in the double slit to make the interference pattern. It's completely obvious, and it's very strange to me that physicists don't turn this situation around and say, what is it about the experiment that makes it look like particles? They usually do it the other way around. They try to say, well, it really is particles, and they say, what is it about it that makes it look like waves? And then you end up with collapse of the wave function. So I knew straight away, just from looking at the double slit experiment, that they had it backwards. And that very obviously led to the loading theory. I knew the loading theory 40 years ago. And then I looked up papers and I saw, oh, well, Lenard thought of something similar to that. Planck thought. I found all these other people who thought the same way, because it was obvious to them, just as much as it is obvious to me, that there was a loading theory going on. So then it was just a matter of finding, well, what's the best experiment to show the distinction? And then I found out that it was a lot more than just showing that there are wave properties and there are particle properties. It was about this collapse of the wave function, that people interpret it as if it's a particle and it only will show up one way or the other. Like even in the double slit experiment, that it would just show in one place to the elimination of all the other places. So I learned that, maybe I learned that in school when I studied formal quantum mechanics, that, oh, they really do think that crazy. They really think that it's like that. Well, from that, I knew the beam split experiment was the way to sort it out. I looked up other people's beam split experiments, found all kinds of mistakes, and guessed that there had to be another way to do that experiment.
Yes. So in the tandem experiment, uh, we are not really splitting the beam there, right? At the
It
end,
is
we are just
energetically, it is splitting the beam. It's not
oh,
sending it
oh,
in two different directions, but it's splitting the energy into each detector. It's splitting the initially emitted gamma ray. Some of the energy will go into one detector, then to the other. It is splitting the energy. It's just not splitting the direction. You don't need to send it in another direction.
oh,
But it doesn't
oh,
matter
yeah,
anyway
yeah.
because I did the experiment as a splitter also. It just doesn't work as well, but I split it with detectors over to the side several times, several different detectors. That worked best when I used the high purity germanium detector. But it's hard to do. You have to go get liquid nitrogen, and it's very stressful. That it lasts about a week when you buy it in a big bottle that I have, and I haven't done that
Hmm.
in in uh, in 18 years or so. And but I did it several times and it took two of them. I have two of those. I was very lucky to find those detectors. They're expensive, but and even used, they weren't that cheap either. I mean, I spent $1,000 each on them, and I was lucky to get it at that price on eBay. Gambling. It was all a gamble. I didn't even know if they would work when I bought it. I just did it because I thought it was
Yeah.
important.
Yeah, that's usually the way that you don't really know what's at the end what is happening when you get the experiment going. And strange things, of course, is that you also had really many failures at first, but you believe that it still can be done and repeated it
That's
for
right.
many years.
That's right. There were failures at first where I just saw noise and had to try different isotopes. Um, it wasn't so long. It, I don't remember how many failures. I, but you see, I had all this theory to back me up. I had good theory at that time. I had some idea of what to do. And it was equally nervous to attempt to split the alpha ray. The alpha ray that took more equipment. I had to build a vacuum chamber and find the special detectors for them. And I think I did more work on the alpha ray than anything else. It was so sensational. I went and I rebuilt the whole vacuum chamber 3 times, 4 times. Uh, I didn't know how big it should be or anything. I overbuilt it at first, where I would adjust all the angles and distances, and so at first I did it in this 3 foot diameter chamber that I was lucky. I found it from some friends of mine. They were giving it away at Stanford University, and I had a friend's truck haul it in. I rebuilt this coder vacuum chamber, and then found I could just make it all smaller. Rebuilt it, and I finally rebuilt it down to a little bottle that's like 3 inches across. It worked the best. So it worked amazingly. And I tried that with all different kinds of metals and foils. and geometries, whether the detectors were like this, or reflecting this way and that way. I tried a lot of stuff. And so the final thing that I show you in my paper, that's after I tried it maybe 20 different ways. And dimensions and sizes, and different detectors. All of this stuff was tried many different ways. So if I'm sort of burnt out at this point, maybe you could understand. I've been through a lot.
Yes. I usually think also that when we get to read the like the final results from the papers from the scientific peer-reviewed papers, we don't really see the struggle and all the phases that that people went through when they did the experiment and all their like before they got the final product of the paper. So that gives to me it kind of gives a little bit false impression of what is going on there. Of course, you can't put all the 20 years work, all the data where you failed. You can't put it on a paper because it would be 1,000 pages, 100,000 pages, and and so on. But we often get a little bit faulty picture and impression of what is happening there. There's happening so much.
Well, it's important to do short, succinct writing. And that last page that I sent you, which was a YouTube comment on somebody else's video, right? I tried to give that as an example.
Us.
Say again.
It was us. It's about Bohmian pilot wave theory.
Right. That was one of the ideas they examined. And I was trying to tell them, look, you didn't examine the loading theory, which was by done all these people. So I tried to give an example of what I thought was good writing to you, to where you explain some of the history in terms of, well, which people worked on it, and why was it thrown away? Those are the important things. If you write about quantum mechanics, the history of quantum mechanics, it'll end up being too long, and 1,000 other people have written about that anyway. So I was trying to encourage you to stay to the point, stay to the history of the accumulation hypothesis. And so, why is it that the accumulation was thrown out so prematurely? That's interesting history. Now there was one other author, Thomas Kuhn, covered that. I don't know, and then there was Wheaton. Thomas Kuhn and Wheaton are the only two authors I found who explored why was the accumulation model thrown out. It's very strange to me that you see all these papers, they don't talk about it at all.
Yeah, it was a really good summary what you wrote about your theory. By the way, I forgot to ask it about this beam split experiment. When you talk about that they use a polarized photons light that goes to the mirror and then bounces to one direction or goes. What can you explain what is a polarization and it's not appropriate.
Explain what about the polarized beam splitter?
Yeah, about what does it mean to be a polarized light, and also why does it not work in the
All right.
yeah.
Our polarized light, if you're looking straight at it, the electric field is going up and down. So if I try to draw it sideways, you'll have a graph of the electric field going up and down. So that we'll call vertically polarized. Then there's horizontally polarized. The electric field, it's a graph. It doesn't look like this. It's a graph of the electric field that goes sideways. And so you can do that with polarizers, any number of ways you make polarized light. Usually it's a combination of different polarizations where it's not pure polarized. It's never really pure. Most of it is in one direction when it's polarized. Polarized sunglasses are like that. So when light reflects off of a surface, it's usually polarized horizontally, and they use polarized sunglasses to be vertical so that it blocks the reflection from surfaces, and that's why polarized sunglasses work. Because the polarization of the filter in the glasses is orthogonal to the polarization of the light that reflects off of the ground, the surfaces, that's usually where the polarization comes from, and that's why they use polarized sunglasses. So you have polarized light, which has the electric field oriented one way or the other, and then you have a polarizing beam splitter. It's usually a cube, and I can find one and bring a real cube out if you want to see one. I think I have one. Sorry, I just wasted time. I couldn't find it. But it's a cube with an intersection of two. It doesn't matter how they do it, but it's usually built like a cube of glass with a split in the middle, and they coat it. I'm not sure if it's an interference effect, how they coat it. Whatever it is, it'll let through vertically polarized light, but not the horizontal. And it'll do the opposite for the other direction. It lets pass. I have to think about which way it is. I forgot which way it is. If it passes vertical or horizontal, or if it's the other way around. I have to think about that for a few minutes. But it only lets through predominantly this kind of polarization reflecting or transmitting. It's a filter for polarizing, for polarized light. It's a filter that lets through this kind of light or reflects that kind of light. So it's not as if it makes that kind of light. It's a filter for whether it passes it or reflects it. So horizontally polarized light, I think it's the other way around. I think I have it backwards. Horizontally polarized light will reflect. Vertically polarized light will go straight through. So if you have that to begin, it'll make the light go one way or the other at the beam splitter. It's just a trick. They should not use polarized beam splitters in this experiment. It's just crazy to me. I don't know how they can do it. I saw in one of the papers that you sent me where they come right out and they say it's a polarized beam splitter, and they said the wrong thing about it. I should almost try to look it up. They said that it makes the polarization. They had it backwards. They tried to say that it makes it be polarized this way or that way, but it's not true. It filters whether it passes through, whether it's polarized this way or that way. There's a big difference. So they're interpreting the way the polarized beam splitter works backwards. And they have some license to think that it's true to use, that it's all right to use. Clauser comes right out and says that he used a polarized beam splitter, and he explains what he used as a source. They have an atomic beam that comes through the source, and they hit it with a laser, and the laser has polarized light. So it puts out two different H news, and one of them is going to be polarized according to the laser, and the other one is going to be different to it. And whatever they're doing, it emits polarized light by this laser. Because the laser is polarized. I've even used the same laser they used. They showed pictures of it in some other paper. So they have a source that can emit polarized light, and then they go to a polarized beam splitter, and they say, well, there's no coincidences. Well, it beats the hell out of me how they could do such a thing. Of course they won't see coincidences. They won't see it anyway. They won't see coincidences anyway. But they're doing this nutty thing that they keep doing in other experiments to use polarized beam splitters. And then there's this the parametric down conversion thing. That's really how they're all doing it now. And I'm just going to say a few words about it because I have to admit I don't fully understand it. But let me just explain what I think I know about it. They have a similar they have a laser that hits a crystal. And so they're blasting this crystal with a lot of light. And so it's not a one at a time source. And that's really important. It certainly is not, it's not anywhere near like a clean system the way I'm doing where we know it's one at a time with the true coincidence test and all that. It's not like that at all. The blasting with a laser, they have it with two different frequencies that comes out in this down conversion where you add up the frequencies, it equals this initial frequency. So it's like the frequency is down converted from the original. So it's like nu 1 plus nu 2 equals the frequency to start. So the frequency to start is here, and then it divides it down. And so they get these lower frequencies. Then they do the beam splitter, with their cube, they'll divide it. And they'll look at one detector and the other detector. And then here they'll have a detector. So they do a triple coincidence test. They're looking at they're putting this all into a triple input, like a 3-input AND gate. I know my D's look the same as the AND gate, but that's how they do the experiment. And I'm just wondering how they can get away with it, because it's not a one at a time source. So for some strange reason, they're able to try to say, well, when we do this, they call it heralding. But it's the same thing as triggering. It's triggering to see these. And then they see they do not see coincidences when they put it through here. And if you were to look on the delta T graph, I don't know if this is in the field. Can you see? Zero. They do not see a peak in the histogram on this. And they say, oh, well, that's like quantum mechanics. They do it, so it acts as if it goes one way or the other. And I'm just not convinced, because it's not a one at a time source. These things are raging at high speeds, and there are polarizations involved. This could very easily be a polarization routing phenomenon. It could be the same thing that I saw before. They don't say whether this is a non-polarizing beam splitter or not. That's why I really cannot analyze this experiment. I don't have enough information. They don't tell me if this is PBS or not. They've been leaving that information out on many of these papers. Sometimes they'll say it. Sometimes they say if you see PBS, that's a warning. That's polarized beam splitter. And some of the papers that you sent, they did say that.
Yeah, but on some they don't say that.
Right.
But the recent like 10 years they have become quite sure that they can arrange a single photon sources by using some. I think it's right this way, like this down conversion thing.
Down conversion.
Yeah. So they are strongly suggesting that they can make it. They can use statistics to deduce that it's a single source. But there are strange things there, because it can be even lower than single photon, because it's statistics, and you can like a post process and analyze it. So how would you do like use this source in the real experiment then?
Now you'll get lower than chance if you start with polarized light and you filter it with a polarized beam splitter. That's how you get less than chance.
Okay. Yeah.
So that's my guess as to what's going on with the parametric down conversion. That it's polarized here, and they're not recognizing it.
So can how polarization, how it affects to the final result, that you kind of get this quantum time graph. So what is in the polarization that makes it really? Is it easy to explain, or maybe going through other way? What is the other option? How would you make a non-polarized light source? Is it even the
most
gamma
light,
source? It's gamma. It's the same electromagnetic wave. Isn't that also polarized?
right, but I'm not using a polarized beam splitter. That's the difference.
Okay. So the source would always be, because it's light, it's electromagnetic waves. There might be different kind of polarization, but now we come to the detector itself.
Most light is not polarized, but the way they prepare it with their crystals and lasers, it'll come out with polarization effects.
Okay, what does it mean that most light is not polarized?
It means that
Like you get light from the sun and nature of the devices.
yes, all the light we see is a mixture of all the polarizations and frequencies. It's a combination of all different frequencies and directions at once. It's a big mess.
I see. Yes. Polarization, it means that it is quite strictly oriented to some direction. So yeah, I understood it different way. Yeah. Yeah, that's the way it is. Okay. Yeah, it's a big topic because nowadays we get a lot of articles in Nature and in science magazines that uses this information and the experiment from single photon systems. They speak even that the human eye can pick up, could act as a quantum system to pick up single photons, like the frog eye also.
It's hard to do. I've tried to see it. I tried once in a very dark room. I was not able to see such. We did it in physics class where we attenuated the light and we looked at it with the detector. We cooled the detector and we were able to see the clicks coming in one at a time, and then we were able to look at it. I had a good teacher in college where we did these kinds of quantum experiments.
Mm. Yeah, it's good to have those kind of tests in schools. Must be very exciting.
Right, that was the best part, the labs. That's why I went through all the fiery hoops to jump through, uh, all the calculus. And I'm afraid I forgot most of the math.
So what else we got in the list? We had this single photon and polarized light thing, and also the history of your. How did you come to the first experiment? That was interesting part of the history.
Oh yeah, well, there's the power supplies. Did you see what I wrote about the power
Mm.
supplies?
Oh, yeah. You put so the minus and plus 12 is okay, but the minus plus 24 it's a little bit more complicated. I had this order already in Amazon's store, but they run out of supply for those devices, so I had to start again this. And my friend from Ericsson company turned out to be a specialist in these electrical devices, so he helped me to find out a few things. But you had a comment about the other.
Right. Well, I sent 2 emails. The second one is the one to read. The more recent email, where there was a 24 volts power supply, and it was floating. So you need 2 of those. Two 24 volt power supplies, and you wire it so that it puts out plus,
Yes.
the other one minus. And then there was another power supply that gave plus and minus 12. So it looked like you'd get by
yes.
with those 3. With those
Okay,
3 boxes.
okay.
So it looked like you had
Yeah.
it there. And I did not recognize that at first. I had to send a second email.
Okay. Yeah, I didn't see the second email, so it would be okay. So I can forward and progress with these. My friend told that he would help with this to wire up this 24 thing, so I can get both minus and plus. And you can also, of course, send some a picture how to do that. So I will make this order this week or next week, and we will. Okay. Do you think you would have time to look for the essay I wrote? I made
Oh
a lot
yeah,
of things. It's
I
like 10 pages.
I don't know, Marko. It 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 I I'll look at it right now if you want. I,
No,
I don't know what to say
it's
about
okay. You don't need to do it now. But I
that.
just mean that you had those comments earlier that I have picked up those and made some corrections and so on. And if you find something other that is like
Well,
misleading,
Marko, it's too long. It's too much other physics that you're going through. Uh, I it I don't know. I don't know what to say. I gave a good crack at it before. Uh, Look, if you'd like to have another session, I'll edit it right here on the video. I'll talk about what I read.
okay,
It
yeah,
it's
yeah,
it's
yeah.
I
We can
must
do
have
that.
spent 4 or 5 hours on the previous editing, so it's hard to do, and
Yeah,
I'll do it in real video. I'll read your paper. I'll give a running commentary on it. I'll read your paper while I
okay,
have
yeah,
you
that's fine.
listen to me. That I prefer to
Yeah,
do it that way.
yeah,
Uh,
yeah, that's
and
okay to me. We
and
can do it next week.
all right, all right.
Yeah. So, oh, yeah. So it's 8 o'clock. So I need to go to make breakfast and go to work.
I very much appreciate you spending time with me, Marko. I think you're doing fine.
No problem.
Uh,
Yeah, it's
please, I like the way
same
we're
to
keeping in
you.
touch with email. Keep up the good work. Bye bye.
Yeah, you too.
All
Good
right.
night. Bye bye.
All right.